Hello, everybody. Thank you for joining our 17th series of the first seminar series on 1st of February. Thank you all for joining. Today we have Shan Gao from University of Alberta. Let's have a brief introduction. First of all, we have land acknowledgement. We acknowledge the land of the Omni-Reunion Network's head office, which is located on York University. We recognize that many indigenous nations have long-standing relationship with the territories upon which York University campuses are located. That precede the establishment of York University acknowledged its presence on the traditional territory of many indigenous nations. The area known as the Toronto has been caretaken by Anishinaabe nations, the Haudenosaunee Confederacy, and Huron-Wendat. It is now home to many First Nations, Inuit, and Métis communities. We acknowledge the current treaty holders, the Mississauga of Credit First Nations. This territory is subject of the Dish with one spoon wampum-filled convents, an agreement to peacefully share and care for Great Lake regions. In the Super Spreader Seminar Series, we welcome faculty members, Omni-Reunion affiliates, and highly qualified personnel, HQPs, including postdoctoral researchers and graduate students, to showcase their research, promote their ideas, and share their research experiences and establish connection among the various branches of the network. It is a platform to spread scientific knowledge about the One Health research framework and the research progress of 30 plus Omni-Reunion HQPs within the network scientific research community. These seminars facilitate knowledge exchange within the Omni-Reunion and the Emerging Infectious Disease Modeling, EIDM network, and the collaborating scientific community. Today, our speaker is Shan Gao. Thank you, Shan, for accepting our invitation to have a talk today. Shan is a PhD student at University of Alberta under the supervision of Dr. Hao Wang and Dr. Mark Lewis. His PhD study focuses on mathematical biology, interpreting and solving biological and ecological questions using mathematical and statistical tools. Currently, he is attempting to use early warning signal, EWS techniques to tackle real-world problems, including the detection of impending disease outbreak. And he's going to talk about early detection of outbreak using feature-based time series classification for risk-misjudgment reduction. A key determinant of weighing the prevention measures for infectious disease is early detection of outbreak. Once triggered, the impact of an outbreak persists, making the return to a post-pandemic state extremely challenging. In this study, they propose a novel framework using the feature-based time series classification method to forecast the occurrence or absence of an outbreak. They find the impedance difference between the pre-transition sequence and null bifurcation sequences can be detected before the occurrence of outbreak. These distinctions are reflected in 22 statistical features and 5 early warning signals indicators from incidence sequence, allowing the framework to effectively discriminate these two scenarios in synthetic data. All classifiers following the framework show efficacy in handling cases far from outbreak time and accommodating varying sequence length. Additionally, they conduct 3 real case studies involving influenza incidence data from UnitedKingdom, COVID-19 cases from 18 countries, and SARS data from Hong Kong, with one classifier exhibiting consistently good performance on these empirical testing sets. Thank you. Thank you all for joining. Thank you, Shan. Let me stop sharing after this introduction and we wish started. Yeah.
Yeah, thank you so much for the kind introduction. And also
My
thank you for the
pleasure.
thank you for the organization to allow me to share my work here. So I hope you can see my screen well.
Yeah, it is perfect. Thank you.
Okay, so Today, I'm going to talk about my recent work about the early detection of outbreaks using feature-based time series classification for risk misjudgment reduction. This is the outline of my talk. So the public health has been facing with the formidable challenges due to the prevalence and recurrence of infectious disease. In recent years, for example, the whole community has been witnessed the COVID-19 pandemic, the Ebola epidemic in Africa, and some other disease outbreaks. These infectious disease caused health threats and also caused the economic losses. It's worth noting that some infectious disease are showing strong transmissibility or a high fatality rate, while others may not be fatal and disappear very quickly without attracting much attention. Therefore, balancing the risks associated with the new infectious disease and the costs of preventative policies as well as their consequences has been a prolonged challenge. Then we just wondered if we can detect the disease outbreak before it actually happens. If so, we can take proactive measures instead of reactive implementations when it's just too late. And also, mathematically, these infectious disease outbreaks can be characterized as critical transitions. And therefore, when it comes to, the prediction of disease outbreaks can be reframed as the critical transition detection. And when it comes to the transition detection, the early warning signal theory is a significant tool. The fundamental principle behind the anticipation of the critical transitions is the critical slowing down as the system approaches the critical threshold or undergoes a significant change. The time it takes to recover from a small perturbation will then increase. Many different indicators such as the standard deviation, the coefficient of variation, the autocorrelation at lag 1, etc. They can identify the presence of critical slowing down and therefore being used as early warning signal indicators. Despite the success of early warning signal applications in many different fields, many works focus only on the cases containing the critical transitions, while they tend to provide the inaccurate alerts for cases with no transition. And this is not acceptable in the context of disease control and prevention, because we don't want to conduct the very strict restrictions to the people, because it will then become the economic burden, the financial burden. Then to wrap this up, our question here is, can we predict if there will be an outbreak, or in other words, the critical transition at the early stage in the content of infectious disease control and prevention? And here our solution is to conduct the binary classification of two types of bifurcations. They are the transcritical bifurcation corresponding to the disease outbreak, or the null bifurcation corresponding to the normality scenario. Now, let's take a look at the materials and methods we are using for this work. So the time series classification has been a prominent topic in the scientific research. Among them, the feature-based time series classification exhibit an outstanding performance. And as our title suggests, in this work, we are then using the feature-based time series classification techniques. And as you can see, this diagram is the illustration of the feature-based time series classification. Here we have the raw time series. They are the observations. And in our case here, they should be the incidence data. With the raw time series, we can then compute different statistical features from them. And here we have the numeric feature data. And in this example, we computed n different statistical features. Of course, we also have their corresponding labels of each sample. Here, I'm using T to represent the time series with the transcritical bifurcation. And I also use N to represent the cases with no bifurcation. So with the numerical feature data and the corresponding label, we can then train the classifiers using different predictive models. And with the trained classifier, we can go back to our observations, compute their statistical features again, and then make the classification. This will help us to determine what we have right now is the transcritical bifurcation data or the null bifurcation data. However, the feature-based time series classification requires abundant data from the study system because we are using the machine learning techniques to train the classifiers. And in practice, the incidence data containing critical transitions, especially the cases with no transition, are inherently rare because we know that for the data collection of disease with negligible consequences, people just tend to ignore it or overlook it or just discontinue the data collection process. And then we don't have sufficient data to support us to train the classifier. And alternatively, our solution is we can apply the simulated data from dynamic models. This gives us the hope to train the classifier with sufficient data. And this is the overview of the synthetic data we are using in our work. For the blue frame, they are representing the data generation process. For the green part, they are the data pre-processing step. And finally, we partitioned the data into the training set and the testing set with the ratio of 6:1. So yeah, this is the overview of the synthetic data. And now I'm going to talk about some details about this whole process. To begin with, we are using the SIR model, the classic SIR model. The reason behind it is, as you know, if we encounter a new infectious disease, the transmission mechanism behind it remains to be found, right? We don't have the prior knowledge to it, and therefore we cannot establish a relatively more complex model based on the new infectious disease properties, dynamic properties. So we are choosing the very basic SIR model to help us to tackle a little bit at the very beginning stage. And we know that the dynamic properties of this model depends on the value of the basic reproduction number R0. When R0 is smaller than 1, it indicates the system remains in a non-outbreak state, whereas R0 larger than 1 suggests the potential of the disease to persist within the population. So this is the criterion for us to generate these two scenarios of the time series, the transcritical bifurcation scenario and the null bifurcation scenario. Additionally, we added three different noises to the classic SIR model, and therefore we obtained three stochastic differential equations. And here, firstly, we are using the white noise data, And then we also use the multiplicative environmental noise. And finally, we have the demographic noise. So the data we are using is actually generated from these three different stochastic differential equations. So we name them as the white noise dataset, the environmental noise dataset, and the demographic noise dataset. Additionally, we randomly choose the data from each of these three prior datasets, and we have a fourth dataset. We call it the mixed noise data. So in other words, the mixed noise data contains the sequences generated from these three stochastic differential equations. So we are using 4 datasets in our work. And then we are going to pre-processing the data we simulated. As we just recall that we are interested in the prediction of outbreaks, which means for the transcritical bifurcation data, the data points after the transition point cannot be used because they are considered as unknown. Therefore, we choose 400 consecutive data points prior to the transition point for the transcritical bifurcation data. And to maintain the consistency for the null bifurcation data, we also randomly choose 400 consecutive data points in this simulated data. So here, just a reminder, this is an example. The slice data of the non-bifurcation data can be here, or it can be here. It can be anywhere within the time window. So this is how we slice the data. And then for the second step, we need to extract the features from the raw simulated data. Here we have 2 options. The first option is called 22 statistical features. And the second option is the 5 early warning signal indicators. So if you remember the very beginning, I showed you the illustration of the feature-based time series classification. And in our case here, if we are choosing 22 statistical features, the number of the features n will equal to 22. And same for the second choice. Let's take a look at the features we are using here. So this table is part of the 22 statistical features we are using in our work. The reason we are using it is because, based on the previous research, these 22 statistical features exhibit outstanding performance in the time series classification tasks with a very minimal redundancy. And as we can see, they are not the normal statistical features we may think, like the mean value, the variation, etc. They are more complex. And alternatively, we are using 5 early warning signal indicators inspired by the early warning signal theory. Here, the first one is the standard deviation. The second one is the coefficient of variation. The third one, autocorrelation at lag 1, the skewness, and the persists. So these are 5 very common early warning signals discovered before, and they are used in many different fields, and they can successfully predict some transitions in other fields. And here, the trend means, for example, for the standard deviation, when the time series is approaching the transition point, the standard deviation will then increase prior to the transition point. So this is the description of the 5 early warning signal indicators we are using in our work. And finally, we partitioned this feature data into the training set and the testing set. Sorry, this is the summary of the synthetic data we are using. We have 4 data sets. we have the training set, the testing set, each comprises 2 scenarios. Additionally, we understand that the synthetic data is not enough to show the efficacy of our trend classifiers, and therefore we are using 3 different empirical data sets. The first one is the COVID-19 data of 18 countries. For this one, it represents the new disease because prior to 2019, we don't have such infectious disease, right? And then for the flu data of the UK, it represents the recurrent disease because people usually encounter the flu outbreak almost in every single year, especially in the wintertime. And finally, we are using the SARS data of Hong Kong. This one represents the no outbreak situation. For the reason, I will elaborate it later in the later slides. And after obtaining the empirical data, they cannot be directly used in our work. Because as you can see, we have different peaks, and actually we count in for example, for the flu data, people encountered several outbreaks. And then we need to slice the data we need to make it work. Here, for the upper panel, it's the incidence time series. And for the lower panel, it's the estimated effective reproduction number. And in our work, we choose the subsequence of the incidence time series data with the corresponding RE smaller than 1. So in other words, we are choosing this white region subsequences as the testing set in our work. And for more details, for the COVID-19 data of 18 countries, we are using the estimated RE from some previous work. And for the flu data and also the SARS data, we are applying the R package fsting to estimate the RE values. And just one more thing, for the COVID-19 data and the flu data, all the sliced subsequences are labeled as T, because here, after this time point, the system will have the outbreak with the RE larger than 1. And for the SARS data, it's kind of different, because as you can see here, for the left panel, they are the prevalence data of SARS in Hong Kong. And we also estimated the RE for the prevalence data, which is presented in the right panel. Here, as you can see, after 2003, April 24, the RE is smaller than 1 and never exceed 1 anymore. And actually, according to the World Health Organization, they claim that there's no SARS infection being reported afterwards. So in this case, we assume the time series after this time point as the null bifurcation scenario, which corresponds to the yellow part here. So for the yellow part, they are labeled as null. But here we only have 1 time series. This is not enough for the classification tasks. So we randomly choose 1,200 subsequences from the yellow part with the minimum length of 7, which is 1 week. So this is how we get the empirical data with different labels. Now let's take a look at the results we have here. Firstly, this is the box plot of 22 statistical features. Here, the red box plots are the statistical features computed from the null bifurcation data. And similarly, the blue box plots are the statistical features computed from the transcritical bifurcation data. And we can easily observe that these data are not normally distributed. And therefore, we conducted the Mann-Whitney U test to compare the feature differences between these two scenarios. And the results showed that the features of these two scenarios are statistically different with extremely small p-values. Similarly, we also have the box plots for 5 early warning signal indicators. And again, the red box plots are the data from the non-bifurcation time series, and the blue box plots are the data computed from the transcritical bifurcation sequences. We also conducted the Mann-Whitney U test, and again, the results show us the significant differences between these two scenarios across 5 early warning signal indicators. So these two statistical tests give us the hope that we can actually distinguish these two scenarios based on the 22 statistical features or the 5 early warning signal indicators. And then this is the 32 classifiers trained from the synthetic data. Here for the blue part, just remember that we have 4 data sets. And also we have two feature extractions. And therefore we have 8 different feature data sets. Also for the green part, we have 4 predictive models. They are the gradient boosting machine, the logistic regression model, which is a very basic statistical model here. And then we have the k-nearest neighbor, and finally we have the support vector machines. And based on every unique combination of 4 data sets, 2 feature extractions, and 4 predictive models, we therefore have 32 classifiers trained from the synthetic data. And this is the performance on withheld testing data. And here the testing data are the simulated data. For the upper part, they are the classification accuracies. And for the lower part, they are the AUC values of the trend classifiers. Here, the AUC values are representing the area under the curve, under the ROC curve. So as we can see here, all of these values are very close or even equal to 1, which means that all of our trend classifiers exhibit near perfect performance on the withheld testing data set. But we are just wondering, maybe this is just too good to be true, because all of the experiment settings are relatively ideal. And then we further wondered, what will happen if the data are shorter and the data sets we are using are relatively far from the transition point? Because remember that in our previous cases here, we are using the time series with the length of 400. And for the transcritical bifurcation data, they are right before the transition point. They are very close to the transition point. So here we aim to optimize the balance. Sorry about it. What happened? Here we want to optimize the balance between 2 contradicting objectives, the accuracy and the earliness. Actually, the no free lunch theorem still hold. The earliness cannot be achieved at the cost of the accuracy based on the previous research. And then we conducted the rolling window and expanding window experiments. This is the illustration of our experiment settings. For the first column, they are the transcritical bifurcation data sets. And for the second column, they are the non-bifurcation data sets. For the rolling window here, we conduct the experiments within the slice data, which is presented in the red, using the green color. And for the rolling window, we are fixing the window size here. The blue part is the time series we are using for the training and testing process. They are fixed with a length of 100. And then the window is rolling from right to the left, which means the window is more and more far from the transition point here. And therefore the gap, which is the yellow rectangle, is expanding from 0 to 300. For the expanding window, it's kind of different. Here for the expanding window, we fixed the gap between the transition point and the window we are using. So the yellow part is fixed, and we are expanding the window longer and longer. So in other words, the time series we are using for this experiment, they are expanding. We are using more and more data sets for the training and the testing process. And this is the result of rolling window experiment using the AUC values. Here, we are using different colors to represent different data sets we use. And for the first row, they are the 22 statistical features computed from these 4 data sets. And for the second row, they are the 5 early warning signal indicators computed from these 4 data sets. And for each of the column, they represent the classifier trained from different predictive models. And as we can see here, when the time series is approaching to the transition point, the performance will increase. This is consistent with our intuitive because we usually assume that when we are getting closer to the outbreak, something different will happen, right? And additionally, for the 22 statistical features, the white noise data show the lowest AUC values. Meanwhile, the environmental noise data shows the relatively larger AUC values, which means they have a relatively better performance. And for the 5 early warning signals, things are kind of different because as you can see here, for the demographic noise data and the white noise data, they have a very good performance at the very beginning, even though they are very far from the transition point. Whereas for the mixed noise data and the environmental noise data, when they are relatively far from the transition point, they are showing a lower performance, a lower AUC values, but they increase very quickly when they are approaching to the transition point. So this is the result of the rolling window experiments. And now let's take a look at the expanding window experiment. We can observe that surprisingly, all of these classifiers could have the performance of them could be improved rapidly when the length is a little bit longer than the initial setting. So here, as you can see, we start with a length of 5, and the performance are relatively low. And if we add some extra data points, then the performance will increase significantly, and then they can maintain a very high AUC value here. Another thing I observed is if we are using the 22 statistical features, then they have relatively lower AUC values at the beginning compared to the 5 early warning signals, because as you can see, if we are using 5 early warning signals, the initial AUC value are basically near 0.8, whereas for the 22 statistical features, the initial AUC values are between 0.6 to 0.7 for most of the data sets we are using here. One interesting observation is, as you can see here, unlike the convergence exhibited in the 22 statistical features, we observe a slightly decrease for the 5 early warning signals when the time series is very long. Our speculation is that for this data are just too long, and the redundant data, or in other words, the data that are too far away from the transition point, are less relevant to the outbreak, and therefore reduce the classification performance here. And now let's take a look at the performance on the empirical testing data. Here, this table is the performance on COVID-19 in 18 countries. And as we can see here, for the KNN predictive model, we can observe consistently good performance on the empirical data set. And also the logistic regression model also exhibits relatively good performance on these empirical data sets. This is the table for the flu in the UK. And again, just like what we had before, the KNN model again exhibits the best performance among these eight data sets. Finally, this is the SARS data in Hong Kong. And unlike the previous tables we observed, the KNN failed in the classification tasks here. However, for the logistic regression model, some of them still have relatively good or even the best performance on the empirical testing data. So this shows us that when it comes to the classification of the null bifurcation scenario, things have changed, and we will further talk about it in the later slides. The discussion part. So in our work, we show that the incidence sequences are distinguishable using 22 statistical features or 5 early warning signals based on the statistical tests. And also we see that all the trend classifiers can perform well on the withheld testing sets. Additionally, all the classifiers following the framework can effectively handle the cases that are far from the outbreak time, and they can also handle the varying time series lengths, demonstrating the versatility and the practicality. Finally, we see that only one classifier achieved consistently good performance on all 3 empirical testing datasets. Now, if I may, let's go back a little bit. You can observe the red one here. For the COVID-19 data, the performance, the classification accuracy is about 84%. For the flu data, the accuracy is about 96%. And also for the SARS data, the accuracy is 100%. So this is actually the only one classifier showing the consistent good performance across all these 3 empirical data sets. There are some limitations in our work. Firstly, the testing set from the real-life records is highly biased because for the COVID data and the flu data, the samples are all labeled as T. Meanwhile, for the SARS data, the samples are labeled as N, the non-bifurcation. So they are highly biased. The classifiers trained from the KN model outperformed others in classifying the empirical data with the transcritical bifurcation, but failed in the classifying the non-bifurcation scenario. Our speculation here is probably the KNN model is inherently good, has the tendency to classify any input time series as the data with the transition. So the model may be biased for the transition classification tasks. And also for the SIR model, it does not consider the asymptomatic individuals, but in reality, such community takes a considerable proportion in COVID-19. So to answer this question, we expanded the COVID-19 incidence data to 5 times, and then we conducted the experiments, and the results show us that there's no significant difference between the performance of these 2 cases. So in other words, the asymptomatic individuals of the disease does not affect the performance of our work here. Finally, I want to mention that our work does not fully address 2 issues accepting widespread concerns. The first one is when the pandemic will emerge after the onset of the disease. Actually, we partially answered based on the rolling window and expanding window experiments. And secondly, how severe the potential pandemic could lead to if there's no control policies are implemented. Well, actually, for the mathematical modeling, this could be answered by the final size, the final epidemic size. However, we know the final size is computed from a well-established model. But in reality, at the beginning of the disease emergence, we cannot establish the context-specific models to answer this question. So these are the limitations and the discussions of our work here. Finally, I would like to thank the collaborators, Emmett, Russell, and also my 2 supervisors, Mark and Hal. I also would like to extend my sincere thanks to Poria, Tianyu, Reza, Alam, and Russell for the very insightful discussions during this journey. These are the references for this presentation today. That's pretty much everything I want to talk about. Thank you so much.
Thank you, Shan. It was a great talk. You have combination of staffs, and we enjoyed. Thank you. If there is any questions, okay, we see some clapping. Yeah. And please raise your hand or ask, or if it is not convenient for you, you can write it down in the chat. Yes,
Okay,
we have
sure.
a question from Mark. Yes, Dr. Levis.
Hi, Shan.
Hi,
yeah,
Mark.
it was just it was a great talk. So thank you. My question was, overall, do you think your methods are better for the diseases that are newly introduced, such as SARS, or diseases that are kind of appearing every year, but you don't know when they're going to appear, like flu or diseases like that? It seems like there's sort of two kinds of categories: novel emerging diseases and versus recurrent diseases.
Yes. So initially, our interest lies in the novel disease prediction because we don't have the prior knowledge about it, which makes it much harder to make the classification and study the transmission mechanisms, right?
Mm-hmm.
So I believe our work could at least provide some solid information or suggestions for the policymakers to handle the novel disease. Of course, we don't completely ignore the recurrent disease like the flu data. So this is why we also use the flu data to test the performance of our work. But if we have the former information, for example, we have the records of the flu outbreaks in many different areas and in previous years, then we can combine the previous information to build a more stronger model to predict the future outbreaks for this specific disease.
Mm-hmm. Okay, great. Yeah, I know that was my feeling too.
Yeah.
But I think it's still very interesting, even for the flu, which we know is going to likely happen every year, except for very rare occurrences, to know when it's going to happen. because sometimes it's early, sometimes it's late. And so I
Yeah,
think
that's true.
your model still may say something very interesting there, even though it's maybe the easier problem in some sense.
Yeah.
Okay, that was my comment and question. Thank you.
Thank you. There is a question in chat. The recorded will be uploaded on the Reunion site. So you see the presentation there. And there is a raised hand. Yes, Ami?
Well, hi, Shan. It's
Hi,
a nice
Emmett.
talk.
Thank
Yeah,
you.
thanks for such a nice talk. So I have one question is, so you used 22 statistical features. Is there
Yeah.
any mathematical interpretation or any formula for these statistical features? You know,
Yes. Yeah.
because these are very complicated, right?
Yes. Actually, there's one paper to fully study the 22 statistical features, and you can find the mathematical expressions and the corresponding descriptions for each of the features in their work. Since this is not the priority in our work, so I just skip it. But if you're interested in it, you can find the paper to have more information about it. But I have to admit, this is more complex than the usual statistical features we may think. And I also want to emphasize that there's no overlapping between the 22 statistical features and the 5 early warning signals, because after all, these 5 early warning signals are also the statistical features we may use. Yeah.
Okay. So I have another question. So
Sure.
what is the shortest and the longest length you consider for the empirical data in your testing?
For the empirical data, so for the SARS data, since I randomly choose the subsequences from the yellow subsequence, then the shortest length will be 7 days, will be 7 time points corresponding to 1 week. And for the longest one, it's actually random, but based on my experiment here, I believe it's less than 400. No, sorry, less than 200, I think. Yeah.
Is there any performance
And
difference when you use short time length and long time length? Like, is there any difference in performance of the classifiers?
actually, I did some experiment. So I need to split this into 2 parts. So for the simulator data, this could be answered by the rolling window and no, this could be answered by the expanding window experiments, because we are using different time series with different lengths to conduct the experiment, and we can have the result here. So as you can see, they do affect the performance, but as long as it's relatively longer, then we can achieve very good performance on the simulated scenario. However, for the empirical data sets, things are kind of different. So I already conducted the experiments using shorter subsequences. So here, for example, originally I'm using the whole subsequence in the white region, and some of them could achieve good performance. Additionally, we cut the very late data points. For example, I cut the 5 points for the last section, and then we again conducted the experiments, and we observed that the performance is slightly lower, but not too much. Yeah.
Thanks again.
Of course, you're welcome.
Thank you, Shan. Thank you,
I
Ami,
see
for your
some.
question.
I see something in the chat. Let me take a look.
Okay.
Okay, I see.
Is there any comment or question? Okay. Thank you, Shan. I really enjoyed, and I have many questions, but
yeah?
I would ask only 2 of them. First
Okay,
of
sure.
all, thank you. Among 32 classifiers, One of them was super perfect. That was for logistic one, and when you have environmental
Yes.
noises.
Yeah, this one.
Why not thinking to this as the environmental noises and logistic form are very well fitted to each other besides the model we have, you know?
I'm not sure if I get your question here. So would you please say it again? I'm sorry about it.
I mean that among these classifiers, one of them works very well. And
Yeah,
that
on
was
the
regarding,
empirical data. Yeah.
exactly. That was regarding to logistic and environmental.
Yes.
I mean that, why not thinking that that is perfect good, not only because of our model, because it is intrinsically these two goes well with each other, environmental noises and logistic models. You know,
Yeah,
of course, your model is very perfect, very precise, and you know.
Yeah, the reason why it has the best performance among these 32 classifiers remain to be further explored. But for now, my speculation is, firstly, the environmental noise data are more noisy compared to other two data sets. The noise amplitude is larger in our simulation process. So this makes it more closer to the real scenario. And one interesting finding is, despite the other three relatively complex models in the machine learning studies, the logistic regression model is surprisingly has the good performance on the synthetic data as well, and even has the best performance on the real world data. So I'm thinking that perhaps the statistical tools could be further explored to handle such questions. This is my intuitive for such results. So this could be kind of interesting, because sometimes the simple method could somehow provide us better results. Yeah.
Great, thank you. It was really interesting. And sorry, one little question, and
Of
that
course.
is, all your works is for pre-pandemic, before the
Yes.
outbreak, of course. And to just you, because you are very exact, you want to go further, and instead of time span of 400, you just
Yes.
be very near to critical point,
Yes.
extend it to 500, just to make sure that everything goes well. Why not, for just a further check, that is a suggestion, of course, you
Okay.
choose, I think it was in slide 21, I just wrote down, some part of your empirical data, the parts that are referring to before the outbreak. I mean that, are we sure that the part of the data we have chosen is exactly the before the outbreak? How you can be sure about it, you know?
Just to double check, are you talking about the simulated data or the real world data?
The real world data.
Oh, I see. That's a good point, actually. So, for the simulated data, we use the R-noun to distinguish these two scenarios. But in the real world, the R-noun is hard to estimate.
I mean, slide 21, right? I think it was slide 21, sorry. 21, right. So you cannot have all the data. You choose the parts that are for before outbreak, because all your time series and all your scenarios is before outbreak. How you are sure, of course, into the acceptable level that these choosing parts are working? I want to learn that, actually.
So here I'm choosing the subsequences based on the RE values. right? This is basically the very common tool for the mathematical modeling people to determine the outbreaks in the model. So this is why we are choosing the RE to determine whether or not the system is under the outbreak or under the relatively normal cases here. But I have to admit the RE could be inaccurate to some extent, but this could be further studied, of course. But for now, this is our solution to determine to label the empirical data so far. Yeah, I hope this clarifies things a little bit.
Right, thank you. I really enjoyed.
Thank you very much. Yeah.
Thank you for accepting our invitation and to have a talk here. Okay, we have something. Thank you all. Is there any question or comments? It seems others have enjoyed too. Great. Okay, so far no more comments or questions. Thank you, Shan. Thank you all for joining us. I hope you all have a good day ahead and see you on our next super seminar series. Thank you.
Thank you so much.
Bye-bye.
Bye. Have a good one.
Bye-bye.
Thank you.